what I want to talk about today is how to speed up some of the performance bottlenecks in distributed systems. And I should mention that this is joint work with my collaborators at MSR, students I've worked with at the University of Washington, colleagues at various other universities, including KAUST in Saudi Arabia, Johns Hopkins, and elsewhere. And a lot of it is work done with the esteemed Professor Jialin Li. So I usually start out these talks by trying to tell people that distributed systems are important. It seems kind of redundant to say that today while I'm speaking to you from thousands of miles away. So what I want to point out is most of the systems that people are interacting with today are distributed systems, and we're building them as distributed systems because they're just too big to fit on one machine. We need them to be scalable, and we need them to be constantly available because they serve many users. So in order to build these systems, we use distributed protocols that keep data correct, consistent, and available. But there's a performance cost to all of these things. We've known for a long time that any distributed system we build isn't going to be as fast as an ideal single node computer if we could build one that happened to be large enough. Because there's just a cost to communication, there's a cost to replication to keep things available, and so on and so forth. But what's changing now is that we're seeing that distributed systems performance matters more than it ever did before. And that's both because distributed systems are increasingly important and increasingly large, but also because we're seeing that we've sped up single node performance a lot. And it used to be the case that some of the distributed systems performance challenges didn't really matter. That, we used to say, well, we can run this protocol to replicate our data, and it's sort of expensive, but that doesn't matter because we have to write data to a slow disk. And as a result of new technologies that have become available in memory, non-volatile memory, GPUs, FPGAs, programmable devices, we've sped up single node performance a lot, but the gap between single node and distributed system performance is growing. So let me give you a couple of examples. I've done a lot of work in distributed storage. So this first graph I'm showing you here is how fast a key value store we could build using a conventional design when I did this, I don't know, maybe 8 years ago. And I'm going to be mixing a lot of results from different places here. So you should take some of these numbers with a grain of salt. I just want to get across a couple trends. We've always known that there was going to be a cost to replication. So a single node key value store could process a couple 100,000 requests. But if we wanted to replicate that to make sure the data isn't lost or it fails, then keeping multiple copies of that might bring our performance down to about 20% of that. And if we wanted to build a distributed transactional key value store where we've partitioned the data and we can apply updates consistently across different partitions, there's an even larger performance cost. But if we think about some of the latest results we've seen in the last few years, there's been a huge amount of progress taking advantage of accelerators to build faster storage systems. So this graph on the right is summarizing a lot of different work from a lot of people. The first thing to notice is these numbers are a lot larger. If you didn't notice, the y-axis quietly changed from hundreds of thousands to hundreds of millions. And that's because we're able to put storage onto new accelerators. But the more important trend from a distributed system standpoint is that the relative performance, the penalty that's required to move to a replicated system or a transactional system has gotten a lot larger because we're spending more of the time running the protocols we need in order to manage the data. And this isn't just a problem with distributed storage. We've seen similar things happen in even a very compute-intensive workload, training deep neural networks. So this is a result from some of my colleagues who observed that in 5 years, these GPUs that were available on a cloud provider got more than 17 times faster. But for some training jobs, we only got a 1.4x speed up. And that's because there's more time spent doing distributed communication. And this is a particularly extreme case. We'll come back to that and look at what some of the results are for a wide variety of workloads. But it really illustrates the fact that distributed systems performance, the communication, the coordination, really matters. So what's going on? Well, in the last few years, we've seen the widespread deployment of things like FPGAs and GPUs that make single node performance, compute performance much higher. And we're also seeing new technologies like non-volatile memory and other kinds of accelerators being deployed. And what that means is that as single node compute performance increases, we start to see distributed systems performance being the bottleneck. So what my group is asking is there a distributed systems accelerator that we could build in order to speed up the communication and coordination side of these systems? And I want to argue in this talk that we can achieve this using in-network computation. So this is something that is quite possible today. We have reconfigurable programmable network devices like programmable switches and FPGAs. They're available now. They're deployed in the data center, and they're designed to run high performance networking applications. But I'll show you that we can also use them to speed up distributed systems. So my plan for today is to talk first a bit generally about the technologies that we're using and how we should be using them, and then look at 3 systems that solve distributed systems bottlenecks in a wide variety of systems, ranging from replicated consensus-based fault-tolerant systems to speeding up training, ML training workloads, and finally towards addressing data placement in highly skewed workloads. So let me start by talking a bit about the big picture of distributed systems design. Traditionally, it's been completely independent from the design of the network, that when we're designing distributed algorithms, we usually treat the network just as a communication channel, and it's not even a reliable one. It's just a black box that occasionally drops packets. But this isn't, today's data center network isn't your father's network. We've got networking devices that can do a lot more than just forward packets along. And the insight that's motivating a lot of our work is that in the data center, we have the ability to change the network in order to co-design distributed systems and the data center network, that we can place small amounts of computation into the network, which will really let us speed up distributed systems. But the big theme that I want to get across is that we really have to think very carefully about which computation to place where and how to co-design the two so that we can take advantage of what things that the in-network computation is good at and what things can be best be done through traditional distributed protocols. So let me talk about some of the hardware I'm referring to here. There's a few different devices that people are using, and these things tend to have a spectrum from things that are very high performance, capable of high throughput, but have more restricted computation, and things that have more compute capacity, but run lower bandwidth links. So at the most extreme end, we've got programmable switches from Barefoot, Intel, Mellanox, and others, where we can configure the processing of the switch to run a small amount of processing on application level logic. These run extremely fast, right? They can handle up to 64, 200 gig Ethernet links. Also widely deployed, we've got FPGA-based SmartNICs, which have more processing power, but only handle 1 or 2 network links. And there are other architectures as well. In this talk, I'm really going to be focusing on programmable switches because they're kind of the most extreme and most interesting end of this spectrum. We can look a little bit more at the architecture. I don't want to go into a lot of detail here, but the big picture here is that this is a switch with a programmable pipeline. We can configure it sort of like an FPGA. We load a custom bit of logic into it, and to change how it processes packets. In particular, we're able to program the parser so that we're not just looking at IP or TCP headers, but we're looking at application-specific fields. And we can reconfigure the logic in this pipeline, which is a number of stages. Each of them is capable of classifying packets and performing some kind of ALU operations, which lets us change the way that packets are routed and modified. And finally, we've got an on-die memory that lets us do stateful computations across packets, although it's not very large. The bottom line here is that we have a device that is extremely fast. It can run custom logic at the line rate of the system, up to 12 terabits per second. So it's got this very simple performance model. Either your program fits or it doesn't. If it fits, it runs at 12 terabits per second. What that means for us is that, it can process packets with as fast as multiple racks of traditional servers. And this is a single device, that costs about as much as a single server. So this is very powerful. But at the same time, a lot of things just don't fit. So this is not a general purpose computer. In order to be so fast, we have to really restrict the amount of computation that we do, to dozens or hundreds of ALU operations per packet. And the memory is also extremely restricted, particularly in comparison to how much data is flowing through the switch at any given minute. So what that means for us as systems designers is that you might be tempted to just try to take an existing application and drop it directly into one of these devices to use as an accelerator. But that's not going to work because the device is so resource constrained that it won't fit. So our key idea here is that we really have to take a co-design approach. We have to think about what's the smallest primitive that we could put into the network, something that we can carefully define, hopefully general to multiple applications, and put it into this device, and then build a larger system around that. So it's hard to decide which applications are good for use in network computing. We've actually provided a taxonomy in a recent paper that lets us classify these. And the things we need to think about, number one is, will the processing fit into the switch? So in order to do that, we look at how many operations we have compute-wise per packet and how much state the system needs. And the ideal systems will have constant computation, constant state. It doesn't scale with the amount of data that's being processed. Sometimes it's okay if it's linear, but that requires some complicated work. And anything that is quadratic or worse is going to be a real problem. The other thing we want to look at is this an application that benefits from being able to be placed in the network? That is, does the fact that we can do this logic change the number of packets we need to send? That either the switch can somehow cause us reduce the amount of traffic, let us build protocols that have fewer round trips, let us take advantage of the placement of the logic into the switch. So it's hard to look at this just as a generality. So I want to look at 3 applications of how we can speed up systems in this way. So the first one is speeding up fault tolerance. So obviously, when we build distributed applications, we have to worry about server failures. And the standard way to deal with this is called state machine replication, which conceptually is really straightforward. We just make multiple copies of our service, and we make sure that they execute the same operations in the same order. And then as long as the system is a deterministic state machine, we know that they're all giving the same results. And if one of the replicas fails, the others can keep functioning. The challenge, of course, is making sure that we run the same operations in the same order across all replicas. So the standard way to achieve this total order is using a distributed algorithm called Paxos. And the way this works in the normal case is that we've got one of the replicas elected to be a leader, and it's responsible for ordering the requests. When a request comes in from a client, the leader assigns it a sequence number and sends it off to the other replicas. We need to get agreement from a majority of the replicas that they can execute that operation in that order. And once we've heard from that, once the leader has heard from a majority of the replicas, it can execute the request and notify the client and the other replicas of the outcome. So there's two main performance characteristics here. The latency of this protocol is determined by the fact there are 4 phases, 4 message delays. And throughput is limited by the fact the number of messages processed by the leader. It becomes a bottleneck, and we'll see that the throughput scales inversely with the number of replicas. So how can we improve on this by changing the way we think about distributed systems? So the traditional way to design distributed algorithms is to treat the network not just as unreliable, but an adversary that drops packets at the worst possible time. And in traditional networks, there's nothing we can do about that. But in a world of programmable data center networks and in-network computation, that's not really the right way to think about this anymore. What we should be asking instead is, what could the network do for us? So we could think about this as a spectrum of network guarantees. At one extreme, we've got the weak asynchronous model, where the network doesn't do anything for us, and we have to use an algorithm like Paxos in order to provide ordering and reliability. At the other extreme, you could imagine that we could try to build a network that guaranteed that all messages were always delivered and that all messages were always delivered in a total order. That would be really great from an application perspective. We wouldn't need this distributed algorithm to implement state machine replication. The problem is that we're effectively saying we're going to solve exactly the same problem now in the network. And at that point, we're just pushing the complexity around to a place where it's harder to implement. So the question we're asking is this a zero-sum game, or is there a middle ground where something we could do that would provide performance benefits to applications and at the same time have an efficient implementation in network devices? So somewhat surprisingly, we found that there is in a work called Network Ordered Paxos. And the key idea in Network Ordered Paxos is to think about the ordering property and the reliability property separately, that we can build a network that provides ordering, and that will help us build a faster system, but leaves reliability to the application. And that makes sense because we've known for a long time that it's hard or impossible to build a completely fault-tolerant network. So more precisely, the model that we're trying to provide here is something we developed called ordered unreliable multicast, where the network guarantees a total order of messages. So if I receive message A followed by message B, nobody's ever going to see them in the other order. But it doesn't guarantee that everyone else will receive every message, because there could be failures in the system. The reason this kind of ordered unreliable multicast is interesting is because it's actually quite straightforward to implement using in-network computation. So the basic idea is that we designate one of the switches in the network as a sequencer. And the sequencer has a very simple job. It just puts a monotonically increasing message counter into a packet. So it's maintaining a counter for each replica group in the system. And we make sure that OUM messages are forwarded through the sequencer, which just increments the counter and writes the value into the packet header. And the result is that if the receivers can look at these sequence numbers and detect when packets have been reordered or dropped. So this is a pretty straightforward thing to do, right? It requires keeping a constant amount of state and performing just a simple addition operation. So it's about the simplest thing that we could imagine implementing in a programmable device. But at the same time, it means that we've changed the model of the network from being completely unordered to being ordered but unreliable. And as we'll see, that has a big implication for how we can design a replication protocol. Just to give you a quick example of ordered unreliable multicast, here we've got two senders sending messages concurrently. And as they get forwarded through the sequencer stamps a sequence number into the packet. Here we're seeing the messages being delivered, and the receivers can verify that they're receiving the messages in the same order. Some of the messages might get lost. This one got delivered to only 2 of the replicas. But when the next message comes along, message number 4, what happens is the replica in the middle can see it got messages number 1, 2, and 4. So it knows that it must have lost packet number 3. And that means that the replication protocol can then go and do whatever it needs to do to figure out what happened to that message. So how is this useful? Well, first off, it's totally ordered, right? We know that the replicas all know that they're receiving the same message in the same order. They know that message 2 should be processed after message 1. They don't have to communicate with each other to decide that like they normally would. Second, we have this drop detection property where that middle replica noticed that it didn't get message number 3. It knew it lost a message and it knew what message it lost. So that means we'll be able to do explicit coordination only when messages are dropped in the network, which is a relatively rare case. And so we took this protocol, this network model, and we used it to build a new protocol called network ordered Paxos. Network ordered Paxos is very simple and very efficient. Clients just send the request to all the replicas using OUM. And the replicas verify that they've received the right message in the right order. And if they do, they just execute it and respond back to the client without having to coordinate with each other. The client just waits for a response from the majority of the replicas, including the leader. And in addition to being very simple, this has great performance properties. The latency is down to 2 message delays instead of 4. Obviously, this is the theoretical minimum. And we also, the replicas aren't communicating with each other, so there's no bottleneck. Each one of them is processing only 2 messages, which is going to give us much higher throughput. Obviously, there's a lot of failure cases we need to think about. You know, what should happen if a message gets dropped? We know from OUM that we can detect the drop, but we have to make sure that either all of the replicas recover the message and execute it, or none of them do. And we also have to worry about what happens if the replica fails, if the leader fails, if a switch fails, and so forth. In the interest of time, I'm not going to go into any of these details. They're described extensively in a paper. But the high-level point is that we deal with this using distributed protocols that look a lot like traditional Paxos. And this is an example of the co-design approach. We've optimized the common case by using specialized hardware to implement in-network computation. We're using traditional distributed protocols for failures in the uncommon cases. And that's more expensive, obviously, but we don't have to do it very often. So let me just demonstrate to you that this not only gives us a theoretical performance improvement, but a real one. So here we're thinking about a cluster of 5 replicas. And we're looking at a graph showing both the latency and throughput trade-offs. So in this case, down and to the right is better. Traditionally, we've had a variety of options. You know, classic Paxos is here in the middle, but we've had other options that were optimized either for latency or throughput. And these, would give you better latency without a throughput benefit, or better throughput at the cost of higher latency. Since network ordered Paxos has this optimized protocol that takes advantage of in-network computation, it can do better in terms of both latency and throughput. In fact, it's beating both the latency optimized and throughput optimized versions on both of their metrics at the same time. Here we're getting close to a 5x improvement in throughput and 50% reduction in latency. So this is an exciting result. But I think what's even cooler is we did a comparison against an unreplicated system. This is one that isn't fault tolerant. It just has 1 copy of the data. And as you can see here, the performance of network ordered Paxos is mostly indistinguishable from this unreplicated system, even though it provides really strong fault tolerance guarantees. This is something we didn't expect to be possible when we were building this, but it sort of makes sense if you realize that we've cut both the latency and the message cost down to their theoretical minimum. And again, this is a result that wouldn't be possible in a traditional pure distributed systems approach. It's really taking advantage of the co-design with in-network computation. So to summarize, network ordered Paxos is a new approach to state machine replication based on this co-design idea. The key here is that we're using in-network computation to build a very simple packet sequencer that lets us speed up the common case, but we leave reliability and fault tolerance to traditional distributed protocols. And we're able to get latency and throughput close to an unreplicated system, which shows that we can build a strongly consistent fault tolerant system without a performance cost. Any questions on network ordered Paxos before I move on?
I have a question, if I may.
Yes.
So that has been a very nice part and very nice plot at the end when it shows how the NOPaxos beats the computation in terms of latency and throughput. How was this experiment conducted? Were there any failures introduced, or it's on pure like no failure?
This is a cluster, one rack in our lab at UW. There are no failures in this case. We can look. We can look at the failure cases as well. They're described in the paper. In general, it's a quorum system. So if some of the replicas fail, but not all, but not enough to impact the availability of the system, the performance impact is pretty low. If there's a failure of the leader or a failure of the switch, we do have to run a view change protocol, and that gets handled fairly quickly, but there is a performance cost.
And the second question I have, so maybe that's just the choice of the name, but what's specific about Paxos as a consensus protocol that it works so well under this optimization with network accelerators? I mean, could you have done the same for or after PBFT? And what should be the properties of the protocol to be accelerated this way?
So, I mean, in general, right, there's the consensus protocols all kind of look very similar, right? Paxos, Raft. I tend to think of it more as view stamped replication myself, as befitting my own background. Really, one way to think about what we're doing here is that we're taking a leader-oriented Paxos protocol, like multi-Paxos, Raft, or view stamp replication, and we're optimizing it so that the role of the leader is so simplified that it could be placed in a programmable device. You could imagine trying to do something similar for Byzantine fault tolerance. I suspect that would be much more complicated just because of the need for cryptography, but we've looked a little bit into that, but not too far.
Thank you.
Hey, Dan, so there is a question from on the Zoom chat. Let me just repeat the question. So the question is there a single packet queue on the switch? I assume that's concerning the ordering properties on the switch, or maybe it's concerning.
Right. Yeah, I mean, so there's multiple queues on the switch, certainly, for quality of service and things like that. We are assuming that we're able to assign a total order of the packets that go into a switch. And that's something that can be done using the programmable switches we work with. So they're pipeline based, where one pipeline handles many ports, and each stage in the pipeline at any given point is only processing one packet. So there is a total order in the sense that the packets are being processed in an order. Now, obviously, there is more complexity when we start thinking about larger switches that have multiple pipelines, or if we want to use multiple active sequencers, which is something that we're actively working on now.
Cool, thanks. Any other question from the audience?
Well, before I move on to something completely different, I want to mention that there's plenty more that you can do with replication and distributed algorithms like this, taking advantage of in-network computation. Just to mention a couple things briefly, we can build replicated systems where the performance scales with the number of replicas. Traditionally, the protocols we saw have throughput that scales inversely, 1/n, with the number of replicas. So adding more replicas hurts your performance. What we'd really like to do is build something where it's order n. And many people have observed that you could do this if your workload was read mostly and you sent reads to just one replica. But this is something that isn't actually correct in general, right? There are cases where if you did that, you would get the wrong result. But a trick we can pull is that we know it is safe to do that sometimes. We can read something if no one else is trying to concurrently modify it. And if we use a programmable switch that keeps track of which objects are currently being modified, we can use this optimization that's normally not okay by running it only when we know it's safe. And that lets us build a system where the throughput for read requests scales order n with the number of replicas rather than falling off order 1/n, or as in the case of NOPaxos, just staying constant. And we've also applied this network sequencing approach to distributed databases. So we can run strongly consistent transactions using a sequencer-based approach, using a protocol that looks a lot like network ordered Paxos. And that can speed up databases, a distributed database by up to 35x. And there's lots of other applications here. But unless there are any questions, I'll move on to something completely different. Okay, so I want to switch gears now and talk about solving, about machine learning. So obviously, if you've been paying attention to anything in the world lately, you've seen that machine learning has been amazingly successful. And a large part of that success comes from the ability to train really huge models on really huge data sets. Building these models is a huge job. It requires large distributed clusters running with millions of compute hours. Building these complicated models can really be a significant capital investment costing millions or tens of millions of dollars. So there's a huge incentive to make this efficient. One of the things we've seen is that distributed training hasn't kept up with single node compute performance. So that might be a sort of surprising thing to say, right? That ML training can be a distributed systems problem. But isn't this a classic compute bound workload where really the only question is how many GPUs, how much money can we give NVIDIA to get as many GPUs as possible? And that's a large part of it, sure. But it turns out we're seeing that communication is becoming a big part too, because GPU speeds are increasing faster than network speeds are. That we've seen a 10x improvement in GPU speeds in the last couple of years, whereas a 10x improvement in network speed tends to take between 5 and 10 years, if not more. So let me show you how the fraction of time spent waiting for communication across the network has been increasing for a lot of training workloads. In a lot of cases, this means that we've got these very expensive GPUs that are sitting idle waiting on data to be moved. Now, this depends pretty heavily both on the cluster we're using, like the hardware configuration, and the network that we're trying to train. So we looked at this using an 8-node cluster at MSR, using a variety of deep neural networks. These include things like for image classification, recommendations, NLP, image transformation, click-through prediction, so a wide variety of stuff. And obviously, this depends, the amount of time spent in communication depends a lot on the structure of the network, on the size of the model, various other things. But sometimes it's really non-trivial. We've got one neural network where we're spending more than 75% of our time doing communication. And in a couple other cases, more than 25%. So this is non-trivial. But I do want to mention that this is something that gets worse as GPUs get faster. And our particular cluster here happens to be using P100 GPUs, which are 2 generations old, though we're running it on current 100 gig Ethernet. We know that the latest generation of GPUs are roughly 10 times faster, say. So to give you a very quick, a rough understanding of what this would look like if we had a faster GPU, we can simulate this by, instead of making the GPU 10 times faster, making the network 10 times slower, switching to 10 gig Ethernet. This is a little bit of a rough approximation, but we'll see that it holds up later with a better analysis. And in that case, we really start to see the network bottleneck getting a lot worse. We've got quite a few networks where we're spending the majority of our time in communication. And that suggests that if we can do something about this network bottleneck, it'll give us an important benefit. So what's going on? Well, let's think about how distributed ML training is usually done. And here I'm going to describe the basic batch parallel training approach. There are other more advanced things that could be done, though most of them are also communication intensive as well. So conceptually, we've got a large set of training data, say a bunch of images, and we'll divide that up among different workers. Each of these workers has a local copy of the current model, and in our training job, what we're going to do is each worker is going to pick up an image out of its local set, evaluate it on the current network, figure out if it classified it correctly and what it needs to do in order to make the network better for classifying that image. And then it produces an update to the model reflecting that. Now, the challenge is these 2 workers have produced separate updates, and at some point we need to merge them. So they need to exchange their updates. This doesn't have to happen after every image, but it does have to happen fairly often so periodically we have to exchange this model update, which is roughly proportional in size to the size of the model among all of the workers, so that they know what the other ones have done. And this has to happen relatively often in order to maintain statistical convergence. And the other thing that's happening is that as models get bigger, the amount of data that needs to be moved goes up. So we're seeing models now with hundreds of megabytes of updates that need to be exchanged. In some cases, this can even get into tens or hundreds of gigabytes, although the largest networks have to use more complicated training strategies for other reasons as well. So the problem is this aggregation phase. What's going on in this aggregation phase, conceptually, is that each worker needs to send its model update to all of the other workers so they can compute the average. Now, this isn't actually an n-squared all-to-all communication in practice, because there are various strategies like parameter servers and ring all reduce that will speed this up. But regardless, it is a communication intensive process. And as GPUs get faster and models get bigger, we're increasingly pushing the training speed bottleneck into the network. So what we've been asking is, can in-network computation help us out here? And the insight behind our SwitchML project is that we don't actually need each worker to learn the model update that's produced by each other worker. All we want is to know the average, or the vector sum of the updates, so they can apply that. And so if we could ask the switch to perform this sum computation and do this aggregation in the network, we'd have a much simpler communication pattern, where rather than having to do the conceptual all-to-all aggregation, all of the workers send their updates to the switch computes the sum and distributes the up the result to all of the workers, which is at least a 2x improvement in number of messages from existing work. Now, although conceptually this is very straightforward, we're asking the switch to do addition, it's actually a pretty challenging computation problem. Part of this comes from the fact that the switch computation and storage is so limited. We're asking it to do addition, but it's floating point addition. And we're asking it to do addition of pretty large tensors. In fact, one of the problems we run into is that the model size exceeds the memory capacity of the switch ASIC. And that's kind of inevitable because in order to make it so fast, the amount of memory we can place on the switch is so limited. So what we have to do is build a streaming aggregation system where we don't try to fit the entire model into the network. Instead, we take this model, maybe it's a few hundred megabytes in size. We divide it up into a few chunks that are tens of kilobytes. And the switch maintains a pool of aggregators that aggregate individual chunks. So the workers will stream updates to these of chunks. And once one of the aggregators receives an update from every worker, it can then distribute the sum to all of the workers. And once it's been received by all of the workers, we can reuse that slot in the switch for the next aggregation in the model. And this is what lets us do an aggregation computation on something that doesn't fit in the switch's memory capacity. One of the other challenges we have to deal with is limited compute capacity. What we really want to do is floating point operations. And we've actually explored a number of ways to deal with this. The current approach that our SwitchML system uses is to convert the floating point numbers to fixed point integers on the host side, and then add those on the switch side, which does require some additional logic to figure out what the right exponent for our fixed point integer is. But there's actually a number of other options. And one of the cool things about the fact that we're working with programmable devices is that we can explore some of these other options pretty easily. So for example, we've got some ongoing work that does floating point logic on the switch itself. And there's a lot of research going on in the broader community about new floating point representations optimized for machine learning, trading off precision for improved dynamic range or sharing an exponent across an entire block of entries. And we've been exploring ways that we can implement that in our SwitchML system. And we were able to do this because the programmable device lets us try out new forms of logic without having to develop new hardware for it. Okay, so does this actually help us? Well, we did some experiments, again, using our 8-node cluster, where we're going to evaluate how much we can speed up the batch processing part of training. So this is everything involved in training except for data loading. And so this is our cluster with 8 machines, 100 gig Ethernet, P100 GPUs. And we're comparing here against NVIDIA's Nickel library with RDMA, which is the state-of-the-art communication library that's used by a lot of systems today. So again, we're looking at a variety of different networks. The benefit we get, the speed up we get varies. Some of the networks like Deep Light were highly network bound already, and we can speed that up by quite a bit. Some of them were not network bound, so there's no real speed up there. But recall that this is something that's going to become more important as GPUs get faster. So we're able to simulate a GPU that's 10 times faster than our P100. That puts it roughly on par, we believe, with the latest GPUs that are available today, although they're very hard to get a hold of. And if we look at that simulated GPU, that changes the compute to communication ratio and makes the benefit of in-network aggregation much larger. Again, it's still not a benefit for every every workload, but for a lot of them, we're seeing up to a 2x throughput improvement in training, which, considering the size of these jobs and the cost of the clusters that run them, is really very valuable. All right, to summarize this part, we've been seeing that even compute-intensive workloads can be bottlenecked on cluster communication. In-network aggregation lets us optimize the communication pattern that's being used for these training workloads. And one of the challenges we have to deal with here is that because of the limited resources of the device, we again need to think very carefully about how the application, the host logic, and the in-network logic and the communication protocol all fit together. It's very much a co-design approach. Are there any questions about the SwitchML work?
Okay, so there is one question on Zoom chat. Okay, let me just repeat that. So that's using the switch slots to do the aggregation affect number of iterations for model convergence?
So the streaming aggregation, the slots, that doesn't really have an impact on convergence. We're doing the same computation you would anyway. The part that does have somewhat of an impact on convergence, although we haven't, or that could potentially have an impact on convergence, but we haven't seen this happen in practice, is that we're doing a fixed point computation. We're doing fixed point math rather than floating point math. And so we've actually tested a variety of different, we've tested this variety of different networks. We haven't, for the most part, the training loss curves look indistinguishable. There's a paper available on my website where you can actually look at the convergence behavior of these in one of the appendices. But definitely this is something we think about, as we've been exploring floating point representations and talking about whether we could do things on, whether we could do on chip floating point, or use a different sort of representation. We have tried things that didn't converge.
I guess it's a related question. So you mentioned that the model updates are quite big. So there are a lot of these parameters in them. So is the resource constraint on the switch potentially be a problem because there are very limited memory on the switch? Is it possible to store all the parameters for the updates?
No, as I was saying, that is one of the challenges we have to deal with. We can't fit the entire model on the switch. What we're doing with the streaming aggregation protocol is to compute the sum of the model updates as they stream through the network using only a certain amount of switch capacity. And the fact that we can take part of the model, sum it, send out the result, and then reuse the switch memory for the next part of the model is very important. In practice, the question is, how much switch memory do you need? The answer is, as it often is in network systems, is proportional to the bandwidth delay product, which is, you need to be able to keep that much memory, that much as computation in flight at any point in order to keep the system running at full throughput.
I see. Okay. And does it require all the workers to be mostly in sync to do this streaming approach because they are working on the same subset of the parameters of the model?
It does require them to. I think that the general aggregation approach does require the workers to do their computation and communication roughly synchronously. That's something fundamental to the model. When it comes to the aggregation part itself, just the streaming of the values, the protocol is self-synchronizing in the sense that if one of the replicas is slow, that means that the switch isn't going to be able to compute the full sum because it's waiting for an additional, it's waiting to hear from one of the workers. And as a result, it won't send out the value, which means that none of the workers will send their next piece until they've heard it.
I see. Okay. Thanks. There's another question on the Zoom chat. So considering that now powerful server switches are available, how about using the switch's onboard CPU, meaning having the data plane to forward packets to CPU to do aggregation?
That's a possibility, and it's an interesting one. But there, at the moment, the gap between switch data plane and switch control plane, or even other kinds of CPU performance is just so large that I think this would that would be extremely difficult. You know, on the switch data plane we're talking about here can process on the order of 1 billion packets per second. We haven't built a CPU-based system that can do that. Certainly not without a lot of complexity. I think there is a place for things like this, possibly hybrid systems that combine a switch with an FPGA, and there has been work on doing in-network aggregation using FPGAs, but even that has difficulty scaling to the same level. Again, we're talking about a switch where we can use 16. We can easily use 1600 gig ports, 200 gig on the next generation, and we can start getting. There's some complexity if we go from 16 to 32 to 64, but that's at least theoretically possible. Whereas if we look at FPGAs, the work I'm familiar with on FPGA-based aggregation, you know, is working with something like a 4-port 10 gig device, and it's, you know, hard to build something that handles more than a couple 100 gig ports with an FPGA, even a very expensive one.
Okay, so I guess maybe last question
Sure.
before we move on. So for extremely, this is also from Zoom chat. So
Yep.
for extremely large scale models, for example, a GPT-3,
Yep.
There is a need for model parallelism. Does SwitchML work in this case?
So that's correct. Model parallelism and other things that are not just straight up batch parallel SGD are very important for large models. SwitchML, as it stands, is really designed for just traditional data parallel mini batch SGD. But we have been looking into how to handle model parallel systems, model parallel training as well. In particular, model parallel training is also communication intensive, but the communication pattern isn't exactly the same. And it uses, you know, fundamentally the aggregation we're doing here is an all reduced computation. The protocols people would like to do for model parallel training, there are many different ones, and there's a lot of innovation here, but they often tend to involve combinations of all reduce, all gather, scattering, and multicast. And we're looking at whether we can build a similar system that optimizes these different types of primitives. But that's definitely ongoing work.
Great, thanks. Yeah, for the interest of time, let's move on to the next topic.
Yeah, sure. So I'll do this next one fairly quickly. The last thing I want to talk about is how we deal with data placement, which is one of the major challenges of distributed systems in a context where workloads are highly skewed. So one of the things we often see in life is that some people are more popular than others. And this happens in distributed systems too. There are people who have many millions of followers, and there are people who have many fewer ones, even if their content is more interesting. What this means for distributed systems is that we see a load imbalance. So traditionally, in order to place data in a distributed system, we would map each user to a particular server using something like consistent hashing. And that becomes a problem when one of the users is much more popular than the other, because the server that has to hold Justin Bieber's tweets is going to see a lot more load than the one that's storing mine. And in order to build a system that doesn't get overloaded and meets latency requirements, typically we'd have to over-provision the servers as though they're each holding some of the popular users, which requires wasting a lot of resources and is very expensive. So our approach to solving this problem is to think about it in the context of a rack scale storage system. And if we think inside one of the storage racks, it's usually the case that some of the servers are going to be overloaded because of the skewed workload, but probably the entire rack it's rare for the entire rack to be overloaded, which means there's still some spare processing capacity on some of the servers in the rack. So the approach we'd like to be able to take is to pick some of the popular objects and replicate them onto multiple servers so we can take advantage of the extra capacity on those servers. That would effectively let us balance load in the rack. And this isn't a new idea, right? This is called selective replication. It's been used by a variety of distributed systems. But there are a bunch of challenges to making it work. First off, how do we know which objects are replicated and where they're stored? And how do we make sure that we route requests to the right server? Second, since we've got multiple copies of the data, how do we guarantee consistency among the replicated copies of the objects? This is a particularly challenging problem, and a lot of deployed systems that do selective replication don't even try to solve it. So our approach, called Pegasus, is to build a rack scale storage system that's designed to tolerate skewed workloads by using selective replication with an in-network coherence directory approach that lets us rebalance the load without sacrificing consistency. So the approach we're going to take here is based on coherence directories. And the idea of a coherence directory is pretty straightforward. This is something borrowed from a lot of CPU architectures. Essentially, what we're going to do is maintain a directory that just keeps track of which objects are located on which servers. And if we can send all the requests through this coherence directory, then we can route objects accordingly. So if we've got a request coming in for object B, we can look it up in the directory, see that there are 3 servers that have this, and we can send the read request to any one of them, whichever one has the lowest load. If we've got a write request coming in, well, it turns out we can actually send this write anywhere we want to any subset of the replicas, as long as we're careful to update the coherence directory afterwards so that we know which object, we know correctly where to forward the next requests. So as I said, this basic idea of a coherence directory isn't new. Your CPU cache is doing this right now. But building one that's efficient is challenging, right? We need to figure out where we can implement a coherence protocol capable of handling the entire load of a rack, and how to build the protocol around it to make sure that it's correct, consistent, and still efficient. So given what I've been talking about today, you probably know where this is going. What we want to do is place the coherence directory into the network. In particular, if we think about a rack scale storage system that has a programmable switch in it, the programmable top of rack switch is great for our purposes because it has a central vantage point on the network. All the requests going into and the replies coming out of the system are going through the switch. And as we've seen, these programmable devices are capable of processing the full line rate traffic of the rack. So we use this to build a system called Pegasus. Pegasus is a replication protocol for dealing with skewed workloads using a coherence directory. And conceptually, it's extremely simple. Since this switch is processing all the requests to the rack, it monitors them in order to maintain the coherence directory. It keeps track of which replica has the latest version of every object. And using that, it forwards requests based on the directory. So if a read request comes in, it gets forwarded to whichever replica has the least load that has a copy of the data. And when a write request comes in, we can rebalance it, picking a new replica set for that object from the least loaded replicas and updating the coherence directory. Without going into too many of the details on this, in addition to being very simple, this protocol has a number of really nice benefits. So the first one is that it guarantees the strictest form of consistency, linearizability, which is to say that even though the objects are going to be replicated, they remain consistent. It still looks like, to an external observer, like there's just one copy of the data and all the requests are being processed in order. And it's an extremely low cost protocol because it's being implemented on the switch that can see all the traffic and reroute all the traffic. So it runs in a single round trip. It doesn't block. It doesn't add any extra traffic. Essentially, it has no overhead relative to just routing requests. The Pegasus approach is quite effective at dealing with skewed workloads. So we tested this using a cluster with 28 servers running one of the YCSB benchmarks. And specifically what we're looking at is how many requests per second the system can handle while meeting a latency service level obligation. So we tried a traditional system using consistent hashing. And when we run this on a uniform workload, it's able to take advantage of all of the processing capability of the system and process about 150 million requests per second. But as we start looking at more skewed workloads, here we're looking at Zipfian distributions with various parameters ranging from moderately skewed to extremely skewed. There's a huge impact because in these skewed workloads, some of the objects are much more popular than the others, and whichever server is holding these objects gets overloaded very quickly. So either it's not able to meet its latency obligation, or we need to really throttle back all of the traffic into the system. And this effect is very dramatic, right? We're down to maybe 10% when at the most skewed workload. If we employ Pegasus, which does load balancing and constantly moves the data around in order to optimize the placement of traffic, the placement of objects while still maintaining consistency, we don't have this issue anymore. Because it's doing that, we're able to keep the system running at high utilization, keep it processing all of the requests without any of the servers getting overloaded by creating more replicas of the popular objects. And so we see the same throughput regardless of whether we're running at a uniform distribution or this extremely skewed Zipfian distribution. In fact, and in the most extreme case, we're seeing a 10x improvement in throughput. Equivalently, that means that if you wanted to run this cluster to support an online service, you could use 1/10 as many servers, which is, of course, a hugely valuable efficiency improvement. And this is just one example, but we've seen similar results on a variety of different workloads, read heavy, write heavy, mixed, small objects, large objects, dynamic changes in the popularity of different objects, and so on and so forth. So this is a very robust result. All right, that was pretty brief, but let me summarize. Here we're seeing how in-network computation can help us with a different type of challenge, dealing with object placement for highly skewed workloads. We're taking an existing solution that was hard to implement efficiently and correctly selective replication. And we're building this in a much more efficient way while still providing correctness by taking advantage of the central vantage point of the network switch. It's monitoring all the traffic, so it can easily keep track of where data is located, which servers have spare capacity, and send requests to the right place. I like this example of co-design because it's a case where we're doing something kind of, in one sense, we're building a load balancer, a request forwarder, which is something that we know that networks are good at, but we're doing it in an application-specific way that lets us do something quite unusual to solve a very different problem, the problem of handling skewed workloads in a strongly consistent way. So again, this is another example of co-design between the in-network computation and the application level protocol. Any questions about Pegasus?
Okay, so there is one from the chat. Actually two. Okay, so the first one. Does Pegasus assume that the replication factor is fixed so that it's sufficient to handle the skewed load?
No, so in fact, Pegasus can change for each object the number of replicas it has, up to having one copy of the going from either having only one copy of the object in the rack at all to having one copy of the object on every server in the rack. And it can change this for each object, and it can change that quite rapidly. In the extreme, we can pick a new set of replicas with a different replication factor every time the object is modified. So the system is constantly monitoring the workload to see which objects are the most popular and decide what the right replication factor should be.
Cool. Okay, so the second question. When are the updates being replicated? So otherwise, load skew will build up eventually.
I'm not sure I quite follow the question, but I think what you're asking is how do we perform the replication and how quickly can we do that?
Right.
The approach that we're taking is that we monitor the workload to see which objects are becoming popular by collecting statistics and monitoring which servers are overloaded. And when the system decides that it wants to replicate an object, it does this by notifying the switch that it would like to increase the replication factor. And the next time that object is modified, we can simply increase the replication factor just by saying that when the next write request comes in, send it to, say, 3 servers or 5 servers instead of 1. And the switch can dynamically choose which servers to send that request to based on its monitoring of the load of the system.
Okay, so I think this is a follow-up.
Yep.
So the question is, does replication factor changes only on updates?
The easiest way to think about the protocol is that we only change the replication factor when an object is updated. Obviously, that doesn't work for every workload. In particular, there's a lot of workloads that are read-only, so they're never updated. In that case, we can, we can change the replication factor or move an object without doing a write. You could think of this, if you prefer, as saying that if an object isn't modified, and we need to change its replication factor, we'll just write the same value to the object.
Great. Any other questions on Pegasus? Okay, yeah, I think that's all the questions.
Okay, well, let me just wrap up with a few high-level thoughts about the state of distributed systems. So as a distributed systems researcher, the way I'm looking at this is that we're now in the third era of distributed systems research. When distributed systems and distributed algorithms research originally started, going back to the 70s and early 80s, it was a purely theoretical problem because there weren't really a lot of distributed systems out there. Certainly we didn't have data centers or clusters. And yet researchers built some profound algorithms for consensus, for replication, for fault tolerance. And once we started building large-scale distributed systems, the Googles and the Amazons of the world. It was very fortunate that we had these because these distributed algorithms gave us the tools we needed to solve distributed systems challenges, to build reliable systems at large scale. And often a lot of that time, we didn't have to think too hard about the algorithms because they weren't the performance critical part of the system. But what we're seeing now is that distributed systems are even more important than ever before because pretty much every application nowadays, even your word processor is living in the cloud, running as a distributed system, and we care very much about its performance and its efficiency. And at the same time, we're seeing that the performance of the distributed protocols are also really critical because, as I showed at the beginning, various kinds of accelerators have sped up compute and storage performance, making coordination and communication and running distributed protocols in serious bottlenecks. So this is exciting because it means that designers, and challenging, designers need to think about algorithms, their distributed algorithms, their distributed systems, their hardware and their networks all together and how they interact, which gives us a lot of opportunities to think about the system as a whole and to do some interesting co-designs. Specifically in this talk, I've been talking about using in-network computation as a distributed systems accelerator, which is something that's been enabled by new technologies like programmable switches. They're capable of doing a small amount of computation very fast and very close to the network, which means that we can use them to speed up a lot of applications, but we need to think very carefully about how to do it. I showed you 3 examples, how we could speed up replication, how we could speed up DNN training, and how we could speed up load balancing for skewed workloads. Each of these gives us some pretty substantial performance improvements or efficiency improvements. And they all depend on being able to co-design distributed protocols with network primitives. So thanks everyone for listening. Thanks to all the collaborators I've worked with who built all of these systems that I've been talking about today. I'd be happy to take some more questions about anything I've talked about or anything else.
Okay, so maybe let me ask a question. So a high-level question.
Sure.
So these network switches have traditionally been seen as a like really simple device doing a very simple job of forwarding packets. I mean, it's really exciting to see that we can move some of the computations into these switches. But since you are now at a larger corporation, IT company, so what is this company's view on essentially having these switches to do actual computations? Is that something that people in industry actually want to do?
That's a complicated question. I think, and it has a complicated answer too, unfortunately. I think what we've been seeing is that there's definitely cases where you can get substantial benefits that people would value from using these devices to do in-network computation. There's also a lot of challenges to doing this, obviously. One of them is, we don't have these devices. We have deployed some of them, but it's not like every switch is a programmable device. And even though there is a trend toward building more programmable switches from multiple vendors, they're not all the same, which means that there's a lot of heterogeneity in it. And dealing with that is hard enough as a research question, let alone as something you would deploy in production. The other issue that comes up, of course, is that the main priority is reliability of the underlying network. And that places a certain amount of demands on the what the switch is doing, and trying to add more complexity to that sometimes works against that. So I think one of the research challenges that my group is thinking a lot about is, the research community tends to think about these network devices, and certainly in the work that we've done and that I've been talking about today, we've been thinking about the switch being dedicated to one particular workload. But that's rarely the case. So one research challenge is multi-tenancy, that if we have a device that is running, that is normally handling some network traffic, and we'd like to be able to place the network ordered Paxos sequencer or the SwitchML aggregator onto it, or both. Like, how do we do this combination in a way that we can be sure that it's not affecting the basic network operation? So in other words, we've always wanted resource isolation and scheduling to be a function of the OS. How do we do this for a switch data plane? It's not straightforward to do. We've started looking into that. One other thing I should mention is that, although a cloud provider would love for servers to be completely fungible, any application could be deployed on any server and moved around. That's not always the case. In particular, we do have a lot of applications that run on dedicated clusters of various types. For DNN training, for example, that's sort of essential because you need to have GPU servers, which are not the same hardware as regular servers. And it's often the case that large GPU clusters will have their own networks. So something like SwitchML, in that case, it might be quite reasonable to think about having a dedicated network with ML specific network features, because we already do have such a network. It just doesn't have any of the necessary features yet.
Okay, great, thanks. Any other questions from the audience? Okay, well, it seems like that's all the questions people have. All right, so in that case, well, let's all thank Dr. Dan Wertz for his talk, really good talk, and thanks everyone for coming. And just a reminder that there is another talk in the afternoon, so make sure to attend that talk as well. So yeah, so that's it for today for the morning session. And hope to see you guys later. And thanks, Dan.
Great, thanks for hosting, Jolene, and thanks everyone for attending and for the great questions. It's been a great audience.
All right, thanks. Okay, bye everyone.